So we can handle this a couple different ways. And I'll do it both ways, with the similar triangle pictures and with the geometric means. So whether we use the square root equation or we use the three triangles, it shouldn't matter. We should come up with the same answer both ways. The one thing I do note right away, if this is 4 and this is 5, then the whole thing is going to be 9, 4 plus 5. Okay, I'm pretty sure we can all handle that one, right? Good. All right, let's do the triangle method first. Again, we get 3 triangles. It doesn't matter if you do large, middle, small, or small, middle, large. It doesn't matter the order in which you do them. And I do exaggerate them, so it's very clear what is what. And now I fill in what I know and what I need to know. Let's start with the large triangles. That's one I drew first. Again, long leg, short leg, hypotenuse. That's the way we have to think about this. So in the large outer triangle, okay, large outer triangle, the short leg I do not know. Nothing there. The long leg is x. The hypotenuse is 9. In the middle size triangle, which is this one right here, with my right angle there, the short leg, I do not know. The long leg is 5. The hypotenuse is x. In the small triangle over here, right angle here, the short leg is 4. The long leg I don't know. The hypotenuse I don't know. Now, from this we have to be able to set up a proportion. Because all 3 triangles are similar. We've already established that by angle-angle similarity. We have to set up a proportion. And the proportion is pretty clear. The x corresponds to the 5 corresponds to this point over here, which we don't know. Don't worry about that. We're just going to use 2 of them. So x over 5 equals another pair of corresponding parts from the same triangles, 9 and x. So when I cross multiply, because it's across an equal sign, I get x squared equals 45. So x is the square root of 45, which we then simplify. Square root of 45 would be root 9, 5, so 3 root 5. That's my unknown distance. And there we are. But that's the way we have to set those up. So the people who struggled with those there, I mean, that's really, that's what we're going to be doing on the test. No doubt you will have problems like that on the test. Absolutely. And you can set them up using the similar triangles. Or, if you prefer, the other method of doing this is to use that geometric mean idea that we did yesterday. And again, that kind of comes down to identifying the parts we're looking for here. Let's use this highlighter. All right, this is the x we don't know right here. All right? And that's one of our independent segments. So x equals the square root of the 2 segments along the hypotenuse that share that endpoint. So one of those segments is 5, and the other segment is the whole thing, 9. And you know what? Instead of multiplying that, since 9 is already a perfect square, I'm just going to go ahead and split that up. You can see why this method is often preferred, because clearly it's much faster. But if you don't see those relationships, if you don't see that very well, it doesn't help very much. Most students, I'd say about 80% of students, use the triangle method, because it's much easier to set up, and then you can see where the similarity is, and you get to do something you're familiar with, versus the geometric mean method, which is this with square roots. And again, that's all set up on seeing that common point there. So either way, that's how we do that. Let's do one more. let's choose 17. I had 5, 8, and x. Now, using the geometric mean method, the quick method, if you see it again, x here is my independent segment, so x is the square root. I have two segments along the hypotenuse that have that same endpoint. Well, one of them is 5, and the other one is 8. So that's square root of 40, which is square root of 4 times the square root of 10, or 2 root 10. And we're done. If we use the triangle method, again, we just start by drawing out our triangles. Large, medium, small. I do know the whole side here is 13. In the large order triangle, I don't know the short leg. I don't know the long leg. I do know the hypotenuse is 13. In the medium triangle, the short leg is x, the long leg is 8. I do not know the hypotenuse. In the small triangle over here, the short leg is 5, the long leg is x. I do not know the hypotenuse. So I'm looking for my corresponding parts. I've got 8 and x is one pair of corresponding parts. The x and 5 is the other pair of corresponding parts, so I get 8 over x is x over 5, so x squared equals 40, which is exactly what we have, x to the square root of 40, same solution. Yep. It's not a midpoint, it's just the common point. It's the common point in this particular case, it's right here. In other cases, like back on the previous one, the common point was down in the end. It's wherever these three segments all have the same point of intersection, but that point always has to be somewhere at one of these 3 points in the main hypotenuse. It's never the main right angle out here. That's never this point. And a lot of people, I mean, it's clear the appeal of this method. I mean, it's way less writing and work. But if you don't see it real well, this works very well. It takes longer, but it works really nicely. So don't necessarily jump to this if you're really not seeing it. If you're seeing it, great. It works and it's great. But if you're not, work with the triangles, because that can be a little more obvious once you get it set up. All right. Okay. Well, today we're going to switch a little bit, switch gears a bit, and we're going to start talking about special right triangles. There are two special right triangles we're going to be dealing with. This is section 4 in the book, 7.4. We actually split it into 2 days. So we do one type today and the other type on Monday, and then we put it all together on Tuesday for a quiz on Wednesday. And the quiz on Wednesday is going to cover things like this and special right triangles. All of them work heavily with radicals. So we work with the square roots a lot in this section. The first triangle is what we call the isosceles right triangle, or more commonly referred to as a 45, 45, 90 right triangle, because the angles are 45, 45, and 90. That's why we call it that. But the nice thing about the 45, 45, 90 is because if I know the angles are congruent, then the opposite sides must also be congruent. So it's an isosceles triangle. So I always know, if I know one side, I always know a second. One leg, I know the other leg. The two legs have to be congruent in this triangle. That's what makes it special, which is kind of nice. But what we want to do is, okay, if this leg is x, then this leg must also be x. What is the length of the hypotenuse in terms of x? Well, what we have to do is set up a Pythagorean theorem, don't we? I'm going to call this n for the moment, okay? Let's temporarily call that n. And we set up our Pythagorean theorem. We do our algebra. X squared plus a squared plus b squared equals c squared. So x squared plus x squared equals n squared, right? You with me so far? Anybody not catching how we got that? Okay. X squared plus x squared is 2x squared. Now I don't want to know what n squared is, I want to know what n is, so I have to take the square root of both sides. So n is the square root of 2x squared. But now here's where we have to do a little bit of our algebra stuff again. The square root of 2x squared is the square root of 2 times the square root of x squared. Now the square root of 2 does not simplify, but the square root of x squared certainly does. What's the square root of x squared? X. So the third side of that triangle is whatever the length of the leg is times the square root of 2. And what we've done is we've established a pattern for this triangle. That is a pattern that we're going to use with this triangle a lot. This pattern only applies to 45, 45, 90 right triangles. Only if it's isosceles. But if it's true, then the length of the leg equals the length of the leg, and the length of the hypotenuse is the length of the leg times the square root of 2. Every time. That's the pattern. X root 2. That's a pattern that you're going to want to memorize. You'll use it, if you go on in mathematics, you will use it a lot. That's interesting. I have 2 of those pages. So let's see how that works very easily in a couple rather simple examples. This side is 5, this side n and p. Well, these sides have to be congruent, so n must be 5. And p must be 5 root 2, yeah. But let's prove it, just to be sure. Let's check it. If I were to set up my Pythagorean theorem, it would be 5 squared plus 5 squared equals p squared, right? So 25 plus 25 is p squared. So p squared equals 50. So p is the square root of 50, which is the square root of 25 times the square root of 2. Yeah, it works, doesn't it? And it will work every time on a 45, 45, 90. If you weren't seeing it before. Yeah. Question? Yeah. This is 12, and the hypotenuse is 12 root 2. Yep. See, because all you're doing is establishing a pattern. We're just establishing a pattern, and we're doing that. And we're setting up similar triangles. And you'll see how that works in a second. Because those are easy ones. When the length of a leg is a whole number, it's going to be super easy. Sometimes you even get things, and again, there's the pattern you're going to memorize. X root 2. Sometimes it's a little different. I give you length of hypotenuse. Hypotenuse is 10 root 2. Well, this one isn't going to be so hard to work backwards, because if this is 10 root 2, what must these sides be? 10. Yeah. That's not bad at all. But what if that side's just 8? Oh dear. It doesn't go 8 root 2, 8 root 2. That's not the way it works. What are we going to do? Well, we got a couple choices. Okay, we've got a couple choices. We could set up our Pythagorean theorem. X squared plus x squared equals 8 squared. So 2x squared is 64. So x squared is 32. So x is the square root of 32. We could set up and solve our Pythagorean theorem and simplify. That's root 16 times root 2, so 4 root 2. So we could do it that way. The other way we can do it is using the pattern. And the way we use the pattern would be like this. What I would do is I'm going to redraw my first triangle here. It goes x, x, 8. And here's my pattern triangle. Now since I used x here, I'm not going to use x over here too. I'm going to use n over here. It's n, n, and n root 2. Right? I don't want to confuse things by using x over here too, even though x, x, x root 2 is the way we normally say it. All right? And the way I would look at this, I'd say, oh, 8 equals n root 2. And this is the equations we did last night. This is what we were solving. Divide by the square root of 2. So n equals 8 over the square root of 2, which then rationalizes. So it's 8 root 2 over 2, but the 8 and root 2 reduce. So I can set up a little equation using my pattern, or I could set up my Pythagorean theorem. It's really up to you. Now, in the ones we're going to learn tomorrow, we're going to have to set up equations using patterns. So it might be a good idea to kind of get used to that process. But what we do is I line up, just like I did here at the beginning on the stuff from yesterday, where I lined up the 3 triangles and I found the corresponding parts and I used that to set up an equation or sort of thing, or proportion. Here, it's even easier. I don't have to set up proportion. I can just set up an equation, find the corresponding sides. I don't have to say 8 over n root 2 equals x over n. I don't have to do anything like that. I can just do 8 equals n root 2 and solve a very simple, well, relatively simple equation. Divide by the square root of 2, rationalize, reduce. By using our pattern triangle. And that's kind of the point is that we're trying to get here is using that pattern triangle. Defining the pattern, using it to set up and solve an equation. Because not everyone is going to come out nicely. We can also create a second pattern, and some people catch this really fast. I can also set up a second pattern. If x is over here and this is n and n, we already have that n squared plus n squared equals x squared, right? So 2n squared equals x squared. But I want to get n solved, so I'm going to divide by 2. So n squared equals x squared over 2. Square root of both sides, n is the square root of x squared over 2, which the square root of x squared is x over the square root of 2, which I rationalize. So that's x root 2 over 2. I'm sorry. Yeah. That's correct. So a second pattern we can have here, if this is the whole number, if the hypotenuse is a whole number, the legs are half of that times the square root of 2. Did that work? When this was 8, what's half of 8? 4 times the square root of 2. That's what we came up with, isn't it? So if the hypotenuse is a whole number, then the leg is half that whole number times the square root of 2. Now, if that whole number is even, that's really nice. If it's odd, oh well. If it was a 9, then it's 9 root 2 over 2, or 9 halves root 2. 9 over 2 times the square root of 2. What most people wind up doing in geometry is just memorizing a second pattern rather than having to do the. That's more common, actually, for this one than even setting up and solving the equation. Most people just wind up memorizing that second pattern, which gets us through about 75% of the problems, if we can know those two patterns. Let's practice. This is 14. How long are the legs going to be? Yeah. 7 root 2. Half of that times the square root of 2. This time, now the hypotenuse is 7. So what are those legs going to be?
7 root 2 over 2.
Yeah. So if we know our patterns, they're pretty easy, aren't they? In most cases. Let's just throw another one out there so you don't get stuck on one way. We can flex back and forth. What if this side is 6? Then this side would have to be, and this side is 6 root 2. We don't take half of it in that case, do we? Okay? So the two patterns are different, even though they're for the same triangle. They're just for different situations. And with that, you think, wow, we got this thing licked. Well, yeah, kind of not exactly. Sometimes it gets a little more complicated. Like I said, if you know those two patterns, that'll get you through about 3/4 of the problems. Nicely. But now we're a little more complicated. The numbers, the lengths of the sides aren't nice whole numbers. They're different. 3 root 5. Well, this one isn't so bad. If this is 3 root 5, how long does this have to be? 3 root 5. And this one gets to be 3 root 5 times root 2. But root 5 times root 2 does combine. That's 3 root 10. I guess maybe not so bad, is it? How about this one? Now the hypotenuse is 2 root 6. Well, my pattern says take half of this times the square root of 2, right? What would be half of 2 root 6? 1 root 6? No, not 1 root 3, just half of that. Remember, divide by 2 would just cancel the 2's, not the, right? Half of 2 root 6 would be root 1 root 6, right? So this would be root 6 times the square root of 2, which is the square root of 12, which simplifies root 4 root 3 to root 3. The other way of doing this, using a pattern triangle, would be to go back and say, all right, and here the pattern triangle might be a little easier. My pattern is n root 2, right? So 2 root 6 equals n root 2. How am I going to solve that equation? Divide by square root of 2. I want to get n by itself. Cancels. Square root of 6 over square root of 2 does reduce. That's 2 root 3. Even faster using the equation method that time. Patterns are great as long as the numbers are consistent and simple. Patterns tend to break down when the numbers start becoming unexpected and more difficult. But the equations always work. And the pattern is still there. We can use it. But I think the equation method is a little easier in this case because, again, the 2 root 6 is the n root 2 side. That fits my pattern. So going with the original pattern there may have been a little bit better. We get the same answer either way. It doesn't matter. I mean, you could always go back and do Pythagorean theorem if you wanted. I could say x squared plus x squared equals 2 root 6 squared. So 2x squared would be 4 times 6 equals 24, so x squared equals 12. So x is the square root of 12, and then break it down again. Okay? There's more than one way to get at these types of problems. You definitely have a number of different techniques at your disposal. Whether it's Pythagorean theorem, or this pattern, or for the same triangle, we could, we'll put n there, and that's n over 2 times the square root of 2, or that pattern. If you're going to be comparing a triangle to a pattern and setting up an equation, use this one. You don't want the fractions, believe me. But if you have something simple like this is 10, then this is easily 5 root 2, 5 root 2. But that is one special type of triangle that we're going to be dealing with, the isosceles right triangle. Like I said, on Monday we'll be looking at the 30, 60, 90 triangle. It's the other one. That's my other special one. So, all of these problems today, every last one of them is a 45, 45, 90 right triangle. Some are easier than others. Some you may have to do some equation work with and some manipulation. But we're going to work on this 45, 45, 90, and then we'll get to the next one on Monday. And I think we're going to have school on Monday and everything. The forecast is snow tomorrow, but it's supposed to be nice on Sunday and Monday. Well, cold, but not brutally cold anymore.